If we do know that an Euler path or an Euler circuit must exist based on Euler's theorem, we can then use Fleury's theorem, which I'm probably going to mispronounce that name because it's a bit of French that I'm not super confident in. But anyway, we can use this to a bit more carefully identify at least one path or circuit. What we want to do there is first identify whether the graph has two odd vertices or no odd vertices, where if it has two, we're in the path case, and we choose one, either of them, as the starting point. If we have none, then we're in the all evens or circuit case, where we can just pick any, really. There isn't a specific method to follow along here, where from there, we number the edges as we trace through the graph according to the following rules, where after you've traced over an edge, you erase it and draw it in dashed. So you're going to make it clear which ones you've used in that method, and then when faced with a choice of an edge to trace, first choose any that is not a bridge, where you only travel over bridges if you are out of other options. And for this here, like before, we're just going to take an example so you can understand how this process here can be applied to find a Euler path, or in the case that we have here, an Euler circuit. So for this example, we're going to use Fleury's algorithm to identify an Euler circuit for the given graph. Where the first thing we want to notice here is that we can actually use Fleury's algorithm to be able to find an Euler circuit. That is, you have to notice that the degrees here work. We have degree 2, degree 4, degree 2, degree 4, degree 4, and degree 2. Where from there, we have to figure out some way that we want to initialize this process, some way we want to go here to be able to make this work. Where, like I said, you often want to work in terms of the higher degree vertices as soon as possible because that gives you less chances of having to run over a bridge, but we can be a little bit arbitrary here. So what I'm going to do is follow the path we have given from the outline set up. I'm not going to sort of, what's the word I'm looking for that, improvise like I did with the last couple of examples. We're going to go here from this path starting at vertex A. We're going to go from A to D here for the first one, which is a decently good pick because that means we're going into the vertex of fairly high degree, that is vertex D. And then from there, we don't have a ton of options. We got, well, 3 of them. So we're going to go over from here into C. Make that our second, which is actually a pretty good choice here because we're going from 3 to 4, which becomes 3 then there. So it means that we don't have quite as much of that fear. We're going to do the same sort of thing coming up here to F. So we're going to make that our third choice following along CF. And then from CF, well, now we're getting into a place here where this one's only got 2 left, that one's got 2 left. When we're done with this one, it's going to have 2 left. That's got 2, and that's only got 1. So we might end up wanting to save this guy for a little while, otherwise we're going to get stuck, but we can't actually get there until the very end anyway, so whatever. Here, we don't have a lot of great options then, because we want to avoid getting stuck here, which means we're going to have to end up probably trying to stay on this side of the graph for as long as possible. Best we can do then is F to D. So that's number 4 here, which unfortunately means that we've only got 1 left there, and that's going to be cutting off that bridge, removing D from any sort of meaningful contention, any meaningful conversation there, as that has to be our 5th traveled edge. And then B also only has 1 left, so we've got to follow along B, but at this point we're actually pretty much okay. Because now here at 6, we have 3 left, and that gives us a straight shot to where we're supposed to end up. That gives us a straight shot back to A. So we actually are good from here, that we go F to E for number 7, then E to C for number 8, and our last edge takes us to where we started, takes us back to A, so our 9th selected along this path using Fleury's algorithm is that last vertex, that last edge there from A to C, although technically we're kind of going from C to A to make sure that we start and end at A. If you want to take this and put it in with a little bit more of an arrowed notation to see the path a little bit more clearly, the circuit, maybe a little more specific there, the circuit a bit more clearly, we can do so like so to get our Euler circuit. Where again, going through this process, we hit D a bunch of times. And this should beg the question, can we do something similar for being able to find paths and circuits that only hit vertices once along the way? And the answer there would be yes, we can do that. That's a construction called a Hamilton path or a Hamilton circuit, which is what we'll be talking about in 14.3.